So, now take an example. So, consider a collection of point particle of mass m moving in a circular orbit about a common center, each with the same kinetic energy. So, they have the same kinetic energy. If the only force present is the mutual gravitational force, what is the particle density as a function of the radius r from the center, in order that the density remains constant in time? So, here we have a cluster of particles which is spherically symmetric, and so this cloud of particles attract each other and they are under rotation. So, suppose I say this particle has a velocity v, so that its kinetic energy T is half mv square. So, you see here the kinetic energy of all these particles, all the particles is given to be the same kinetic energy, and they all are attracting each other. So, we have to calculate the particle density, that is number of particles as a function of r, radius, and with time that density does not changes. That means there is a dynamical equilibrium. So, that means each particle is radially in equilibrium. So, let us solve this problem. So, now this is the cluster of particles. So, let us consider this particle m. It has a velocity v, and you see it is attracted by the gravitational field of all the inside mass, that it suppose something. Now, you see, suppose the inside mass is denoted by capital M, then the kinetic energy T of this particle is given as half mv square, that is given as constant, and the force by which this mass is attracted is given by g m m by, now this is just a sphere of mass with total mass m, by this, suppose this distance is r. So, r square is equal to this gmm by r square gravitational force provides the necessary centripetal force mv square by r. So, this cancels out. So, we get g m m by r is equal to mv square. This is 2. So, from 1 and 2 we got this mv square is equal to 2t. So, we will write here g m m by r as 2t, where t is the kinetic energy which is constant. So, here we got m as a function of 2t by g m into r. So, we have dm by dr is equal to 2t by g m, implies dm is equal to 2t by gm dr. This is equation number 3. Now, we got dm. Suppose I consider a small thin shell of this. Suppose this total mass is m. So, dm is the differential mass of that. So, that dm will be given by density rho into 4 pi r square dr. This is dm mass. Suppose I take a small element, concentric element. So, this mass dm will be equal to this rho into 4 pi r square dr. So, we will put this dm here. So, 2t by gm dr is equal to rho 4 pi r square dr. So, here dr cancel and we get mass density as 2t by gm 4 pi r square. We got rho. Now, rho is mass per unit volume. Next, we can write this rho as number density, number of particles present as a function of r, into mass of each one. So, we got n, that is the number of particles present, rho by m, that is 2t by g m square 4 pi r square. This is the number of particles which varies with r like. So, now let us come to example 2, where we will talk about the double star and triple star also. So, in terms of G, L and the masses, what is the rotational period of an equal mass double star of separation L? So, first let us solve for a double star of equal masses. Next, what is the time period of an unequal mass double star of separation L? So, unequal masses double star. Next, what is the time period of an equal mass equivalent triangle triple star? So, we have a triple star of all the three masses which are on the vertices of an equilateral triangle. Next, what is the time period of an unequal mass m1 is not equal to m2 is not equal to m3 equivalent triple star? So, let us find the period of a double star and a triple star. So, now we have a double star, one of mass m and another of mass m, separated by a distance L, and they rotate about their center of mass along this circle. So, since both radius are same, so they are always diametrically opposite. So, that is the case A. So, masses are equal m1 and m2. So, you see, take up this mass. So, the attractive force is G m square by total distance between them is L square, that is equal to m v square by r, radius is L by 2. So, this 1L cancels, this mass cancels. So, we have G m L by, so v square is this, implies v is equal to under root G m by 2L. So, we have the time period as 2 pi r by v, that is 2 pi, r means here L by 2. So, L by 2 is here and v is root over G m by 2L. So, this 2 cancel. So, we have pi L by root over 2L by G m. So, this is the time period of this double star system in which the masses are of equal. So, now let us come to another double star system with unequal masses m1 and m2. So, the total distance is L, but the center of mass, they will rotate about their center of mass. So, this rotates about this and this rotates about this. So, this radius is r1, suppose I say this is r1, this is r2. So, r1 and r2 let us calculate. Now, r1, this distance from the center of mass is given as m2 times r, m2 times r upon m1 plus m2, and r2 is given as m1 times this r by m1 plus m2. Now, let us consider the dynamical equilibrium of this mass. Here G m1 m2 by L square, this is L given, by L square is equal to this centripetal force is m times v1 square by r1. So, this is m1. So, m1 gets cancelled, v1 will be G m2 r1 by L square root. Now, this time period will be given by 2 pi, this whole circular arc is 2 pi r by v1, that is 2 pi, v1 is now, v1 is root over 2 pi r1 root over this L square by G m2 r1. So, we have now time period is 2 pi L root over Gm Gm2 by this r1 is root over r1. Now, r1 value is this much. So, root over m2L upon m1 plus m2. So, this is this value we can simplify is by 2 pi L root over this m2 will gets cancelled. So, by 1 root over L by this G m1 plus m2. This is the time period for a unequal double mass system. So, now come to a triple star system in which all the masses m1, m2 is equal to m3. So, 3 masses we have. So, let us consider this mass, point mass m1 and this is m2 and this is m3. So, we have 3 masses, they are equal masses and they are on the vertices of an equilateral triangle to form a triple star system. The distance between 2 masses is L. So, you see this is, let us find out first the altitude. So, you see this is L cos, this altitude will be L sin 60, L sin 60 is L root 3 by 2, this is. Now, the centroid is the center of mass. So, this distance is 2/3 of this. So, this distance suppose I say r. So, the radius of the circle on which they will turn will be r is equal to 2/3 of L root 3 by 2. So, that comes out to be L by root 3. So, r here r is equal to L by root 3. So, now you see this, just see all will rotate on this circular track with the center as the center of mass. So, consider the dynamical equilibrium of m1. So, we have G m1. Now, the force on this about this is the gravitational force, this suppose F, this is F. So, this is 60 degree. So, we have here this force, the gravitational force, F gravitational force is equal to 2 times F cos 30 degree, that is 2 times F is the force of interaction between them, that is G m square upon this L square. So, this is the value of F and cos 30 is root 3 by 2. So, force due to gravity towards the center of mass becomes root 3 G m square by L square. Now, this force provides the necessary centripetal force so that the star can negotiate that circular path. So, that is equal to, this is equal to, now equate here only to m, that is v square by r, r means L by root 3. So, 1L, 1L, 1M, 1M cancelled. So, we have root 3 G m by L is equal to v square, root 3 becomes this side. So, this cancels out. So, v is equal to root over this we got. So, now time period is 2 pi this r by v, that is r is again you see L by root 3 by v is equal to L by G m. So, this is the expression for the time period of a triple star system. Now, the fourth one, when m1 is not equal to m2 is not equal to m3, this case is left for an exercise for you. So, here what we have to do, this is m1 mass, this is m2 mass and suppose this is m3 mass. So, they form an equilateral triangle suppose. Now, you see their center of mass first of all you have to find out. Suppose this is the center of mass, it is not at the centroid of the equilateral triangle, somewhere here it will be there, and then you have to vectorially calculate what is the force acting along this and what is this position and do the same thing. So, vectorially you have to do it. This is left for an exercise.